Hi there, calculus students. I am at a doctor's appointment today, so I'm not in class, obviously. Today's going to be actually a lot of independent work time where you get the chance to practice some of the related rates things that we started talking about last class. Related rates are really challenging because there's a lot going on, and one of the big focuses of today is to help us get organized as you go. So you're going to need to get out the ladder problem from the POGIL that we did last class. And while you're getting that out right now, just want to let you know that the purpose of you doing this today is to make meaning of the chain rule in world contexts rather than just doing it out of rote memorization. So the purpose is to kind of connect this to meanings rather than just doing the process and not having any idea what you're doing. So as you're getting out your POGIL from last class and kind of looking over the ladder problem, I just want to make it really clear that by the end of this class, you should understand that related rates are related and can use calculus, mainly the chain rule, to determine big aspects of these relationships. We're going to need to use a lot of algebra skills and formulas that you know from algebra to be able to find those relationships. But it's mostly highlighting this calculus chain rule. So you can explain how each part of the equation is connected to the rate. There's lots of things going on and everything's connected to some rate. And you can implicitly differentiate with different variables. So before we implicitly differentiated with x and y, and now we're implicitly differentiating with t. And you can use two seemingly unrelated events and relate them using calculus. So mostly today we're going to do the POGIL, and we'll do one problem as a class before you do that. So you'll also need a notebook paper in order to do these notes with us. And while you're getting out a piece of paper, or you can do this on the back side of the POGIL, I think there's extra space on the back side of your POGIL. We'll do a related rates problem together because I think it's important that you see how a related rates problem could be done. And then I'm going to give you some more independent work time and be able to work through several of these problems. So if you, on the back sheet of your paper, you're going to want to write, make a table similar to what we have here, where we have known descriptions, and so we're going to try and use words to describe different things, an area or a space for symbols or variables, because there's symbolic reasoning that we are going to be using. And then if that symbol or variable has a value, we're going to record it here. And then units are always really helpful because it kind of keeps us in understanding how this is relating to the problem at hand. So I'm going to go over this, and I'm going to go relatively quickly. So follow along if you can, and if you don't, this is posted on mrgermanis.org, so feel free to take a look at mrgermanis.org. So a pebble is dropped into a calm pond, causing ripples from the center. The radius of the outermost ripple is increasing at a constant rate of 1 foot per second. So here's an image that I think is helpful in thinking about what we've got going on here. If I were to draw this out, I'm going to do it actually in red. If I were to draw this out, I've got a circle that drops a pebble, and there's some radius going out from it. When the radius is 4, oh, that's a typo. When the radius is 4, what rate is the total area of the disturbed water changing? So I see area of a circle. It looks like there's a circle. They're concentric circles moving out. I'm going to just write down the area of a circle is pi r squared, because I think that's going to come in handy. So what are some of my known descriptions here? Well, I'm talking about a circle, so I have the radius of a circle. I have the radius of the water ripples out, and we're going to represent that radius of circle. For water, I suppose you could say water if you wanted to. The variable is r, and it's going to be represented with r. And in fact, we're even told that the radius is 4. So that's really helpful for us. And radius, excuse me, not r, 4. And the units of this are going to be feet. This is just the radius, and I think based on this, we're going to be talking somewhere about area. So we're going to talk about area of the circle. It looks like the variable that I'm choosing to use is a, and if the area is going to be square feet, probably square feet or feet squared, square feet, same idea. Well, if the I think that I can calculate this based on information that I have. So if the area is pi times, if the radius is 4, the area is going to be, well, 4 times 4 is 16 pi. So I'm just going to write that in there because maybe I'll need that later. Now, we're talking about rates, and we have a constant rate of 1 foot per second. And that's what the radius is changing. So the radius is changing with respect to time. So dr dt is a thing that we know about. And we actually know the rate, the value of dr dt is 1. And the units are feet per second. And I hope that you can see that dr is the change in the radius is in feet. And time is in seconds. And so it's feet over seconds. Change in radius over change in seconds. And so we'll give a descriptor to this. The rate of change over time for outermost ripple. And if I'm looking through this problem, when the radius is 4 feet, what is the total area? What rate is the total area of the disturbed water changing? So, hey, how do I write? I suppose I'm thinking, how do I write area as a rate? The change in area over a period of time. And I suppose that would be square feet per second. And that's actually something we're looking for. They're asking us to find that. So it's the change in area over time. Okay, so we've got the big pieces, and now I have a lot of things going on, and the thing that I'm looking for is dA dt. Well, where if I'm looking around here, the only thing that I have with A in particular is the area is pi r squared. Well, if I take a derivative of A with respect to time, if I do d dt of A equals pi r squared, I'm gonna get dA dt, which is what I was actually looking for when I was starting to do the problem. So dA dt, derivative of A with respect to t is equal to pi. Pi is just a constant value. The derivative of r squared is going to be 2r to the first power times dr dt. And now I have all the pieces parts I need to find dA dt. I know pi is just a constant. I know the radius is going to be 4. Dr dt, we are told, is 1. And it looks like I didn't need to do this right here, but it was nice to have it available to us if I did need it. So all I'm going to do at this point is plug in different values. So pi times 2 times 4. The radius is 4 times dr dt was 1. So this looks like, sorry, this is way off in the corner. 2 times 4 is 8 pi. So the value here is 8 pi. And that's how quickly the area is changing over time. Big procedure, I know. If you need to review this is on mrgermanus.org, and I've put it there. There's also another video about related rates that I hope that you can utilize. All right, so we talked about this last class, and this is just a reminder of the sliding ladder problem. So it might be a good idea to just pause the video and kind of, for five minutes or so, or 3 to 5 minutes, just to take an inventory of all of the stuff that we did last class. What I'm going to have you do is there's some work in the POGIL just to kind of remind yourself about what this is, but I want you to just kind of look at your work and understand what it is. So what I'd like you to please do is at this time, I'd like you to please stop the video. Please stop the video. So that we can, for 3 to 5 minutes, just so you can go over the stuff that you want to in this, so we can move on and be productive with it. All right, hopefully at this point you've got a chance to go over it. What I'd like you to do is, at your pace, and I really want you to focus on understanding more than anything else, I want you to try and work on questions number 4 through 7 to support your thinking and how you can work through the ladder problem. There is an answer key with the substitute that I left so that you have access to the information, but I'm not going to spend time in a video going over it. So please make use of this time. It's really important that you make meaning rather than just doing a bunch of steps. So this is another perfect opportunity for us to stop the video so that we get some work time for questions 4 through 7. And I think that you should stop for, I think 4 through 7 could take anywhere from 15 to 20 minutes. But I'm not entirely sure, so if students are working faster, then you can move on, and if not, then you can slow down if you need to. But we're going to go over problem number 8 in just a moment, which has a lot of challenge to it. All right, so POGIL number 8 is about a balloon, and I believe in your POGIL you have access to number 8 that has this table already written out for you. I think this table should look familiar if we've followed along in the last couple of problems, because it helps you organize a lot of different things that are happening. This particular problem is very, very common, and it has to do with helium in a balloon growing at a constant rate. And so I've actually drawn a picture that hopefully you can see down here. This volume of this balloon kind of looks spherical, and for the most part we don't really count the air that's in this little section over here, but the radius of the volume of a sphere comes out from the center, and we have an equation for the volume of a sphere. I'd like you to give this a try for about 15 minutes. I'm really focusing on the descriptors, the variables, any information that you know or can easily find out from the contents of the problem, and then units that you have to go with it. If you're feeling really stuck, problem number 9 helps you go through this step by step. So again, I want you to pause the video, and maybe this is near the end of class. Take this home as homework, but we will spend some time going over this here real quick, and maybe if not, near the end of class. So please pause the video to do this problem on your own first, using number 9 as a support if you need it. All right, hopefully you've had a chance to go over this problem. If you have not gone over this problem yet, you can watch this video, but it won't be very helpful because when you struggle through something for a few minutes first, it really helps your understanding once all of the pieces are coming together. So I'm going to read the problem just again, just to make sure that I'm fully aware of everything that's going on. Helium is leaking out of a spherical balloon at a constant rate of pi cubic feet per second. That seems interesting, important to know. What is the rate of change in the radius of the balloon at the moment when the volume of the balloon is 33.5 feet cubed, or cubic feet. We've got an equation for the volume of a cube where v is a variable. It's a variable with relationship to the radius. The volume is a relationship to the radius of the sphere. So I suppose some things we know. We know the radius is something that is going to be important. We've given it a value of r. Right now, I suppose we can figure out what r is in just a moment. Let's see if we actually need that. Radius is going to be in feet. These are very large balloons. They're probably weather balloons that go up in the sky. We know the volume, I suppose. The volume of the balloon is something that's changing. Of balloon. And it is going to have a volume of 33.5 feet cubed. And we're told that up above, 33.5 feet cubed. And I know that I need the rate of change in the radius. So I know that I need dr dt. And so to get that, I'm probably going to take, so this is the rate of change in the radius. I know that the rate of change in the radius is going to be feet per second, because it's usually the rate is in, the radius is the rate, or excuse me, the radius is the thing, and it has units of feet, and then it's changing every second, so rate per second. And then I'm going to get a change in volume, I suppose, the rate of change of the volume. So I'm probably going to get dv dt at some point in time, the rate of change in volume. And that's probably cubic feet per second. Looks like I have a lot of missing information. Oh, actually, I know that the helium is leaking out of the spherical balloon at a constant rate of pi cubic feet per second. So rate of change in volume is negative pi. And it's negative because it's leaking out. It's going down. The rate of change of the volume is decreasing, which means that the rate of change of the radius is going to also be a negative number when we get there. So the next step, I suppose, is to take the derivative implicitly of this this character of the equation. So we're going to get dv dt. Ooh, I do not like it there. We're going to do that somewhere else. We're going to do dv dt. We're going to take that first one, and then 4/3 is just a constant, so it's going to come along for the ride. 4/3, and pi is also a constant. R cubed, the derivative is going to be 3r squared, and then it actually looks like I can cancel and simplify this. Times dr dt. I almost forgot about the chain rule there. That would be bad. All right, now it looks like I do need the radius of this guy. And how do I find the radius at a certain point in time? Well, I've got a formula for it. If I know the volume is 33.5, all I need to do is solve for the radius. And when I go and I solve this and I multiply both sides by 3/4 times 3/4, those cancel out, divide by pi, and I take the cube root to undo this r cubed, so divide by pi, that goes away, and I take the cube root. The radius ends up being approximately 2. Approximately 2. Now, I went through that really quickly, but it's just algebra to solve for radius, and you can do that on your own. I'm not going to spend video time on that. But at this point, we're looking for dr dt. I've got a formula. I now have all of the pieces. I have dv dt, which is negative pi. I know that it's 4/3 pi times 3 times r squared. I know the radius is now 2 because of the work that we just did, and we're solving for r dr dt. I'm probably going to zoom out here in order to do this with all of the information that I have. So I'm going to use this, and I'm going to just clean it up. dv dt equals 4, the 3's get canceled out, 4 pi r squared dr dt. and I'm just going to plug in things that I know. dv/dt for my table is negative pi. 4 is 4, pi is pi, r is 2, so it's going to be 2 squared, and dr/dt is the thing that I'm looking for. Okay, this is just, now it looks like it's just actually solving for dr/dt, which is just going to be a big division problem. So I'm going to divide both sides by 4, 4 pi times 2 squared is 4, so 2 squared. So 4 pi 2 squared. And then if I simplify, I get dr/dt equals, the pi's are going to cancel out, negative 1 over 4 times 2 squared is 16. Negative 1/16. So negative 1/16 feet per second. So this is a mighty large problem, and I'm glad that you stuck around, and I hope that I didn't confuse you. We can go over this if you want when I come back. For homework tonight, there are 2 things that I want you to try, and I don't want you to spend too much time on them. Number 10 is just reading, and number 11 is I want you to spend no more than 20 minutes on it, and we're going to review this when we come back next time, and I will go over any problems that you have. There's tons and tons and tons of resources, mainly videos, on mr.germanus.org. Please take a look at those. I spent a lot of time making them for you, and I think that they are valuable. It just takes related rates takes a lot of practice. Thanks for hanging in there. Have a great day. I'll see you next time.